Let's see if I'm live. I'm waiting for it to go live. Hello, hello, hello. Go live anytime now. There it is. Okay, we're live. Hello, hello. Go live. Okay. So, first of all, people think that just-in-time is interpreted. This program right here, TempleOS, has no paging, and it's ring 0 only. All memory is accessible. All memory is read, write, execute. So we are free to put code into anywhere in memory that's within range. We are free to put code, and then we can call. Where did it go? There's the call. This calls a function that's at a variable address. Anyway, the interesting thing to note is this is a very primitive compiler. It grabs 512 bytes off the code heap. The first 2 gig of memory is called the code heap. That's because you can use a call, the simple call. Anyway, it's a lot simpler if you put all the code in the first 2 gig. But normally you have stuff other than code in memory. Code is not usually the biggest source of memory. Anyway, like your graphics and stuff are. Anyway, so the point here is what we're doing is a stack machine, reverse Polish. Have you ever used a reverse Polish calculator? You go 1 and then 2, and then you hit plus, and it adds 1 and 2. Anyway, this is a expression compiler. Okay, so I did 1 plus 2 plus 3 times 4 times 5. You can take my word for it that this is 64-bit machine code right here in this column. This is machine code. If you want, we can look it up in the data sheet, and we can verify that these are in fact the machine codes for x86 64. Some people are stubborn and they spread misinformation, like they'll start saying, oh, it's bytecode, or no, this is machine code. This is this little program here is a compiler of expressions. The reason I made it is to show that it is possible to make a compiler that's not an interpreter. This is actual machine code. We are putting machine code. This is a tiny compiler compared to my my full-size compiler. Well, in the compiler directory is a full-size compiler, and at the back end you'll notice these ICUs. Anyway, intermediate code U32. These are storing machine code into the final output. Okay, so that's what some people look at. You know, like the elephant with the blind people. They look at different parts of the compiler. In the optimizer, they see where I'm evaluating constants. If you have 1 plus 2 in a program, well, you replace it with 3 in the compiled output. That looks like if you think about it, when you evaluate a constant in order to simplify it in a compiler, it looks like a virtual machine or something. So I have a big case statement for all the different intermediate codes. They call this IR, intermediate representation. I don't have a what do they call it, AST. I don't have a symbol tree. My compiler is a stack machine. So I don't have a symbol tree. I do it with a stack machine. Anyway, directly. So now I don't make a lot of compilers make assembly language and then assemble the assembly language. I just make machine code directly from the intermediate IR. So I don't make an assembly stage. So I think my compiler is fast. I haven't really benchmarked it. It can do 100,000 lines in a second. I don't know. The most of the time is taken writing the file. So it's kind of well, anyway. So we're going to operate just in time. That's why my compiler has to be fast. So if we go in the games directory and we go, this is the eagle diving for fish. If you hit F5, so we don't have object files and we don't have executable files. We just have source code and F5 to run it. Except it's actually you can hit character return include, and now we it's the same process. So first of all, we have a compiler that is just in time or ahead of time. As a matter of fact, just in time is easier for a compiler. It just is. Anyway, so if we say the Commodore had BASIC at the command line. I'm just going to show you something. On the Commodore, you would do stuff like you would, at the command line, you'd say print hello 20 go to 10. You would do something like that on a Commodore, and it would be right in memory. The kids today cannot imagine anything else other than a Unix or DOS interface. And then if you said print like that, the BASIC program would execute immediately. If you said print 1 plus 2, the BASIC would execute immediately. Print 1 plus 2. It would execute immediately. So what you had is if you put a line number, it stores it in memory. If you do a statement without a line number, it executes immediately. And that's how the BASIC worked. Well, TempleOS is the same, but it's with C. I had to make some changes to the syntax of C. So if I say, this is what I always do, count I64N, I64I. So we're just going to count up to N. And now if we say count, okay, so at this point I just entered a function. It's just like how I entered a basic function, and then if I say count to 10, it calls it, and that's just like a print statement by itself. So if you enter a function, then it waits for you to enter it all, and it compiles function by function. So I think I don't know if other compilers do that. I guess they do. This compiles function by function, and if it hits a statement outside of a function, it executes immediately. Well, holy shit! Guess how we make programs. We use 0 main. Now you might say, don't you need arg? No, we're using the same rules. The compiler just included that. Whoa, what do you think that did? Whoa, what if we say, what? Okay, what do you think is going to happen with, well, anyway. Okay, so we said what as the first statement, then we compiled a function and we said main, and that's going to call the function. So I'm going to include that. We got what, hello. Now what happens if I type main? Okay, that's a function. Now what happens if I say main I64I, and I say colon %d, and I say comma I, and I say 1 2 3 4. Now we got hello 1 2 3 4. Now if we say main 5 6 7 8. Now what is it doing? We say trace main 1 2 3 1 2 3 4. So what is it doing? It's pushing 2 3 4 and calling, and then this is main, and it has source code links, and that's if it's we don't have source code links to the count function. If we say who minus r, this is our environment. Oh shit, I didn't do minus r. Yeah, I did. This is this is the same process that included the flight simulator. So this is all the flight simulator functions and variables. And if we go to main, oh, that's anyway. So I'm gonna hit Shift Escape. Now we killed that task. Now you can either hit this or hit Control Alt Escape. If you get a lot of stuff, you might want to do that. You don't really have to. If it just overshadows, if you repeatedly include, it overshadows the old versions. So what if we want something like standard C? What you do is you say ... and what ... you know this variable in C++, guess what? For I equals 0, I less than argc, I plus plus %, let's do x, comma, argv sub I. Okay, what did we just do? ... causes of this variable, except it's called argc and argv. Okay, those are anytime you say ... you get argc and argv, and so let's include that. Now if we say main 1 2 3 4 6 7 9 or so. Okay, so that's how we get argv and argc. So what if we wanted to add them? Now they're you might ask, what if we say main hello world? These are string constants. They're just going to be addresses. It's up to you to what if we say %s? No. Oh shit. Okay, so exit. If that doesn't work, you got to reboot. Okay. So what did we do wrong? We did this wrong. What? So escape. Now we said what? Now we say main. Okay. Now I have my puppy. He wants into my room. Now what? Oh, puppy. Okay. So puppy is in the room. Now, what are we doing? Let's go ahead and look at how this compiles. Trace on, oops, trace on, okay. Main, what? Okay, this gets trickier. It's a variable argument function, so this tells how many. There's one. All pushes in if you're in 64-bit long mode, all pushes are 64-bit regardless of what they claim to be. So this pushes a signed byte of 1 that's 64, that's extended to 64 bits. This pushes an address. Now you might ask, what is that address? Look at this, 38B9, 57, 68, there's the ASCII. So when it compiles, it puts string constants after the code that it's compiling. So if you have a function and you have string constants, after the code is where string constants go. This seemed like the obvious answer for me, but this is shocking and revolutionary because everybody else has segments. I don't have any of that segment shit. They have to sit there and hold on to it and rearrange it into pretty data segments and code segments and stuff. I don't have any of that hassle. So my code is so clean. My compiler is clean as a whistle. Everything is really clean. Now if you want to do inter-process communication, I already, okay, Control Tab, Alt D. Okay, Alt D, let's do Alt H. So, guess what? Oh, that's pretty silly. I won't do anything silly. There's a task called Atom. Everybody's a child of Atom. And so if you can make stuff global in atoms, like if I say Atom, hey Atom, make variable age. Age equals 1, 2, 3, 4. Then if I go down here, age 1, 2, 3, 4. So we're both children of Adam. Task rep. The indentation is who's a child. So we're both children of Adam. Now these are kill. Like if you want to, what is that? That's got. Here's the task. So in the upper title bar is the task. 5C28, 5C28. Now this, if we hit Control T, we can see what this macro does. It says kill, and it's got some code there that it's going to execute. It's going to compile just in time and execute. It's going to compile that just in time. It is so easy to start up the just in time, compile some stuff, and drop it off. Okay, we just killed that task. You might ask, why don't we include headers? Well, we inherit the symbols of our parents. So everybody's a child of Adam. If we say who recursive, this is the default, by the way. Holy shit, this is Adam's symbol table. All those, basically you get the entire operating system stored in the symbol table of Adam. I don't know if you would want all the symbols in Linux, but this is small, and it will always be small. It doesn't just get bad when it gets bigger, it gets worse. It doesn't just get good when it gets smaller, it gets better. Scaling up makes it terrible. Scaling down makes it awesome. You idiot, he's worried about scaling up. You should worry about scaling down. Teach people to scale down. It's a lot harder. If you think you're clever because you can scale up, you should see somebody who can scale down. Anyway, so we don't have a make. How can we live without a make? Well, we got 100,000 lines a second. We can compile this puppy, just including all that stuff, we got 8 gig. It's not like the old days when you had limited memory and 5 users. What the hell? We can compile. We don't need a linker. We just compile this shit. You want to see me compile it? Bow! I just compiled the kernel and the compiler. No, the way I did it is I have a in my account files are in the demo account directory. If you hit control in the demo account example, here's my account files, and distro has the ones for compiling the distribution and stuff and config. So control D is the file manager. So distro. So what do? Make OS install boot. This this calls make OS, which is the kernel. This loads up my my configuration. When you say make OS install boot, this hits some as it's compiling, it hits some executable code that prompts for stuff. We want this on, when this is done, it's going to be the C drive, and we want to automatically mount some drives in the kernel. So we want the CD drive, we want to probe P. Hey, whoa, that's weird. What the f? Okay, we hit 4 for hard drive and enter. We use the default disk cache. We know default options, enter. So I just compiled the kernel and compiler. Basically, there's only 2 modules that are ever compiled ahead of time: kernel.bin and compiler.bin. Find files starting at root bin star. There's kernel.bin, compiler, compiler.bin. Then there's a couple others in the boot directory. This is the CD-ROM boot kernel. This is CD-ROM. This is the CD-ROM kernel.bin. That's if you're making. You see, if you're making a CD-ROM, you don't want to overwrite your own kernel, so you store it temporarily there. This is the boot sector stage 2 old master boot record. You save it anyway. So you never need to do ahead of time compiling unless you're tinkering with the kernel or compiler. How can I say that? Well, look at this here. Let's look at a application after Egypt. Okay, so the default or the convention is you make a load file that includes everything, and you make a run file that loads and then executes. You see the statement outside of the function executes, and then these are source code files in here. So if now watch this. So that's in the application directory. Now let's go down onto our this is if we go to home, personal menu, you access it with Control M, and it's a document, and these are pictures with a payload of code. If you hit Control T, include, so it's really everything fits together beautifully with this. We have a just-in-time compiler. We can kick on and off. We can compile a little chunk here and there really easily. So after Egypt, so this is going to this pop-up, this plus PU stands for pop-up. So we're going to make a new task and then do this include. This is kind of a subtlety. If you don't do that pop-up, it's going to do it in the same task. So let's see what would happen if we can even notice. So first of all, let's do the. I can click on the graphic if I want. Okay, so that's a game. Now I'm going to hit Control T. I'm going to get rid of this pop-up flag, hit Control T. I don't know if this is going to work. It should. Oh, you know what? I think we need a +X. Let's put that on there. This is a macro automatically has a +X. This means exit the menu and go back to the. Right now we are in a task. We process, if you want to call it, it's a task. And so far we were at the terminal and then we entered the menu. Now if we hit F1, now we're in the editor and we're editing the part of the help. If we hit Shift Escape, we're back to the menu. You see these popping up and down along the side? Okay, so if I say +X, then we exit the menu and do the macro at the next level out. So let's see if that works. Okay, it doesn't have a carriage return. That's kind of interesting. So it shelled. Now we're back out to the terminal, and okay, now if we quit, we're back at the command line. This is the original task. We say who -R. Okay, these are all the this is all the code compiled just in time for the program. So if you'll notice, I already I didn't save the document, so we have pop-up is back. It doesn't save automatically. So what this means is these icons cause a new task, they compile the payload, and then when they're done, they're killed. And so this is the way you run if it's the normal way you run an application. Okay, so so somebody was looking at the exec function is not very common. So let's just say this is getting silly. Exe print. Okay, let's do something. This will blow your mind. U8 star code. Exe print. We can just say %s, or we can just say code. Let's say %s. What we are going to do, there's a family of functions for print. This is the family. They all have the variable format and argument, and each one of these does something. grprint prints a graphic, it does the printf with the graphic, it does printf with graphics mode. Let's try that. Let's see. How about let's do a combination. grprint, the device context is first, and then we say code. Oh, we do xy. Say 100 100 comma code. Now this is %s code. Then we're going to compile, and this is going to compile it and run it just in time. Okay, so we don't have to call it. It's called main. Let's call beep. Okay, so code beep. It used the graphics layer. It executed the code. So our compiler is so fast and so ubiquitous. We can even use it for the HTML. This is like we have a document format. If we say red in $signs, then now our text is red. Okay. Now watch this. What if we say red +1? It's blue. Okay, that's not too exciting. Let's say $sign red +2. Control T. Now it's green. Now let's say green +1. Now it's blue. Blue +1. Damn it. Blue. What is your problem? Blue +1. Oh no, we can't do that. Yeah, we can. No, 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 no. What am I doing? That's not how it works. Foreground, comma, 5 + 3. What am I doing? Oh, it's crazy. Oh well. Now it's light gray. If we say light, the reason this will always be 16 color, and I dug in, and there's no way you are going to make this operating system something else. These are the colors are anyway, what was I doing? Okay, so you can the compiler is invoked to parse the DAL docs all the time. In other words, they're full of the C compiler is used all the time. Like this, these are macros over here. This is a macro. CD home. Watch this. Just for grins, let's put beep inside of the command. Now this is web. Okay, now I can even use the mouse. It's gonna beep, and then it did a change directory, a beep, and then a directory. So so we can oh, that's on the graphics window. Okay, let's do song. How about my song? Let's do play st. Okay, so we do include. Now we say my song, C, D, E, F. Okay, that croaking is because VMware puts too much distortion. QEMU doesn't put enough, and VMware puts too much. Okay, so what can we do? How about now this is kind of deceptive because we don't normally have that loaded in memory, but let's do a Control L. In other words, that song is only if we have included the file. So what if we want to make it? Let's do that. Okay, so let's reboot. Okay, we just rebooted. Now what do you think is going to happen? Nothing. Okay, so if we want to make a DLL, then we put it into home packages, and we say include home test. Now we reboot. Now we say my song. If we want 8th notes, 16th notes. Okay, so that's how you make a DLL. That's no big deal. That's right now it's in atoms. Memory is associated with a task, so that when the task dies, it gets freed. And we just put that into the Atom startup code. So during when it boots, it starts in the root directory. It starts compiling start OS. This includes the headers for the kernel and compiler. Those are compiled ahead of time. And then it goes into Atom and does make Atom. And then finally it goes into Home and does make Home. So Control D, all this code is compiled during boot. How much is it? We have, if you look down here, this is the lines of code compiled. There's been 47,000 lines compiled. Now if we compile the kernel and that's the just-in-time code. Now we just did the ahead of time. So there's about a total of 100,000 lines of code. I'm going to take that out of my, did I do that already? I wasn't paying attention. Okay. So it compiles everything in Atom, and then it calls the make home, and if it's not found, it searches the parent, and so there's the make home that it compiles. God, that's probably very confusing to people. It's a nice feature. There's a default file. If somebody wipes out their home directory, it'll use the defaults that are in the parent. Anyway, so what if we want to do a macro? Okay, so I sort of screwed up, didn't I? I had it, okay, Control L, macro, click me, and then the payload for the macro is, oh, we want to do my song. How about GFEDCBA? And then I think we want a character turn. Okay, escape. Now I haven't saved it, so it's going to get wiped out. I can save it if you want. I'll hit Control S to save it. And now I click it. Oh, you know, that's kind of risky. Watch what happens if we reboot. Now, what's going to happen? Nothing. That's because it wasn't included into memory. Now I just included it. Now I hit Control M. Now if I say who -R, we have my song and do it once. Okay, so I'm gonna go. You can edit it here if you want. It doesn't matter. It's the Control S works differently, but Control M pulls up the menu. Control Shift M is, there's two files. Control M is menu, Control Shift M is notes, and they're almost similar. These are change directory commands that I use all the time to navigate, and then I have my icons down here. The original, here's what I was thinking. I was thinking, okay, wow, if I hit up arrow, we don't have command history. Well, that's no good. What am I going to do about command history? And that's when I thought I'll have a hotkey and I'll put some permanent history, frequent history commands. So that was the inspiration. This was going to be my command history replacement. So they're permanent into a document, and then I thought, wow, what if I make pictures and make macros? Wow, that's an icon. So this whole file, this is a document instead of a desktop. You can move these icons. As a matter of fact, you can, all the graphics, the document file is 100% consistent throughout the whole operating system. So I'm going to put those, I'm going to put those on the command line. They still work because they do the pop-up. If they didn't do the pop-up, they would try to shell and get screwed up. Let's take the pop-up off. Here's the pop-up. Now if we hit -X, it'll go to the bottom. Let's do that +X. it'll go to the bottom of the window. Now I think it'll work. Okay, there's no carriage return required for a pop-up, but there is for this. So if I hit enter, it's going to do it, and I don't really want to do it. So now the source code, if you want to, this will kind of blow your mind, but if we go into the source code, this is battle zone. If I have it on the clipboard, so what if I hit escape? Now if I come back in, I just put my icons into my source code. Now this is stored as binary, it's not stored as ASCII. In the file, if I say dump zone out, these are not ASCII files. The top is ASCII, the bottom is binary graphics. This is not a trick, it's genuine, written from scratch. It's not a kludge. There's no trick. It's not a kludge. I've seen, someone was just showing him an Apple thing. So now what about these icons? If they do a pop-up, then there's no reason not for them to work. Look at that. So if they do a pop-up, you can put them in your source code anywhere you want. As a matter of fact, the compiler will ignore macros, I do believe. I don't think it compiles them. Let's hit F5. Yeah, we ignored it. So you can, in your documentation, let's suppose you wanted to display some graphic when you're documenting your code. You can put an icon right in the middle of your code. You can put a graphic image to document your code. You can put links. I didn't show you links. The document format works all the way through the whole operating system. Actually, it's not quite true, sort of. There's only one place it doesn't work. Can you guess where it doesn't work? I'll give you a clue. Start OS. So this starts compiling make atom. And what is make atom? That's the atom directory make. And this starts compiling down here. It compiles the DAL docs, and up here it compiles the graphics. So what if we had a graphic in an earlier file? Well, now that's not going to work. If it's earlier than the graphics library, it's not going to work. As a matter of fact, as soon as the compiler switches over from raw text to DAL docs, at this point, starting at the DAL docs directory, you can the compiler switches over. Then the compiler can do sprites. But as a matter of fact, I had to. The only place in my operating system where there's sprites, there's really no reason for sprites, except for on the wallpaper we have that terminal button. That's a sprite. So that compiles during boot. It's in the Atom directory under wallpaper. Oops. And so that's towards the bottom of the compile, and so it's after the sprites are defined. So I think I put some sprites in the graphic. I'm sure there's a couple sprites in here under composite, I think. No, I put them all in. Did I put them in miscellaneous? There's a couple sprites for. Why would I do that? It used to be a little sprite library. So where there's a special, you see this hand? That hand is a sprite. You can grab, and it's got pan. You can pan any. You can always pan. You can always zoom. You can zoom anytime, any place. You can Control Alt G. You can put a grid and snap, or no, Control Shift G. There's a lot of. So I'm done talking. How about that?